All right, so again, back into half-life. And so what we are going to again end up using is our formula, N is equal to N naught times 0.5 to the power of T over H. Now, here's what we're going to do is that in this case, we have a piece of wood from an ancient burial site has a carbon-14, which I'll explain, which has a half-life of 5,730 years, a radioactivity of 30 BQs, which is a measurement of radiation, becquerels, actually. Now, if the same type of wood just cut down has a radioactivity of 240 becquerels, how old is the burial site? All right, so a little background information here of this carbon-14. Carbon-14 is a radioactive material, but it doesn't hurt you. In fact, it's a good thing because it doesn't hurt us because everybody has it. In fact, every single living thing has carbon-14. Now, you always have a certain amount of carbon-14, or a tree, or an animal, or just, like I said, any living thing. But once you die, that amount of carbon-14 gets cut in half every 5,730 years. So what can happen is we can use this information to figure out how old something is. So in this case, here's the information we have is that a piece of wood is found and now it has a radiation level of 30 becquerels. So that's what it ended up with. But whatever type of piece of wood it is, and they know this kind of stuff, each type of piece of wood has a certain amount of carbon-14. And this particular type of piece of wood, as it's living, has 240 becquerels. Now, again, we're measuring carbon-14, and in that case, carbon-14 has a half-life of 5,730 years. All right, and what we want to know is how much time's gone by. And because of that, then we could figure out how old this burial site is because there's a piece of wood's there. Now, so I substitute in my values here. So I have 30 is equal to 240. All right, times 0.5. T is, we don't know, okay? And then the H value is 5,730. All right, now I want to solve for T. Now it's an exponent. It's in the exponent, so that's going to be key. We're going to have to deal with that. But the first thing I got to do is I'm going to get rid of this 240. In fact, I got to get rid of everything on this side because I'm going to get T by itself. But the first thing I can do is I can divide by 240. And what I do to one side, I have to do to the other. All right, so now what happens is these 240s divide each other out. Now, 30 divided by 240 is 0.125. All right, but now on this side, what I have is a 0.5 to the power of T divided by 5,730. Now, this is a situation that we looked at solving, maybe not with decimals, but we use that looking at using the log function. Because we're solving for an exponent, I have to make that exponent a normal number, and the only way to do that is to use one of my log rules. And so I'm going to take the log of both sides. All right, so I'm going to write down the exact same thing. So I can take the log of 0.5, and again, to the power of 5,730. Now, again, when you take the log of a number, it's always going to be smaller. And when I type the log of 0.125, it's actually a decimal. It's so small that I get negative 0.9. Now, again, the whole reason that I'm using this log rule is so I can make this exponent a normal number. So this is where I'm going to use my log rule and bring my exponent down. Now my exponent's a fraction, so I'm going to write it as a fraction. T on the top, 5,730 on the bottom. And then, of course, I still have this log of 0.5. All right, now I still have this negative 0.9 on this side. I now have to take the log of 0.5. So again, I'm going to write, I got t, I got 5,730. All right, now the log of 0.5, again, very small number. So when I type that in, again, I get a very small number because that's the log function, right? It takes a big number, makes it smaller. Well, it takes small numbers and makes them even small numbers. And if they're really small, it makes them negative. And so now this is what I have. Now there's lots of ways to solve, but from here on in. But what I like to do is I have a number equaling a fraction. And this is something we've had many times. I'm going to create a fraction equaling a fraction. All right, so that I can cross multiply. So now what I have is I've got 1 times this negative 0.3 times t. So there's the one part, 1 times that. I just rearranged the t and the negative 0.3 because when you're multiplying, you can do it in any order. And then on the other side, I have negative 0.9 times 5,730. All right, and so now I'm just going to simplify my right-hand side. So I'm going to leave this negative 0.3 t. And let's see, I multiply 0.9, negative 0.9, I should say, times 5,730, and I get 5,157. And then, of course, my last step is I'm going to divide by negative 0.3. And again, on both sides to get my numerical coefficient by itself. And well, I'm lucky here because a negative divided by negative gives me a positive, which has to happen because I can't have negative time. It doesn't make sense. And if I divide those, I end up with 17,000. Whoops. Let's get rid of that. 17,190. Now, again, as I mentioned earlier today, H and T must be in the same units. So because this half-life is 5,730 years, that's how old our burial site is. Now, again, it's not exact, but they do use this to figure out how old things are. Or what often happens is, especially with global warming happening, is they find animals up very north, Antarctic, that have frozen dinosaurs type, like a woolly mammoth, frozen in ice. And so what they can do is they test that woolly mammoth's radioactivity, its carbon-14 radioactivity, to see how old it is. Now, the problem is with a woolly mammoth is there is none around anymore. So what they use is they compare it to an elephant. They know how much carbon-14 a live elephant has. And so they would take the dead elephant or the dead woolly mammoth and compare its carbon-14, and then they could find out how old that animal is that was caught frozen in time, basically. And actually, they find people too. All right, so our next one. An unknown substance has a radioactivity of 1,350 becquerels. And then 4 days later, the same substance has a reading of 880 becquerels. Calculate the half-life of the material. All right, so again, we're dealing with half-life. So I've got my formula here of N is equal to N naught times 0.5 divided by T, or the exponent of T divided by H. All right, so now in this case, let's check it out. N is that 4 days later, we had 880 becquerels. When they started measuring, at the very beginning, we had 1,350 becquerels. Now, the time that's gone by is 4 days. So it means our half-life here that we're going to find is also going to be in days. All right, so this time we're finding the half-life. All right, so again, I'm going to Substitute in my formula here. So I've got my 880. And then my N naught is 1350. And a little note, by the way, is that your N naught should always be bigger than your N because we're talking about things decaying, shrinking. So your starting amount always has to be bigger than your end amount. All right, so if you're confused on which one's N and which one's N naught, well, the smaller one's always the leftovers, the N. All right, so then I still get this 0.5 here. All right, now this time I got a 4 divided by H. Okay, so now again, guess what? I'm solving for an exponent. But before I do that, again, just like I did last time, I'm going to divide both sides by my N naught, which in this case is the 1350. All right, so as again, these are dividing each other out. Now I get 880 divided by 1350. I'm getting 0.65. All right, again, that's going to equal, I got my 0.5 over here, but it is to the power of 4 divided by H. Now, there's nothing else I can do here. So the one thing I got to do, because I want to get at that exponent, is I'm going to take the log of both sides. So we got the log of 0.65 is equal to, again, the log of both sides here, the log of 0.5 to the power of 4 over H. 4 divided by H. The bad looking 4, bad H. All right. Now, let's see here. So, now again, I'm going to take the log of 0.65. So it's probably going to be a negative number again, real small number. And it is negative 0.19. All right. Now, we're... the reason I'm taking the log again is because I'm using my log rule. So I'm going to have 4, and I'm going to put an H in the bottom. Just give me a second. Times the log of 0.5. Again, put my 4 in here, my H in here. So again, my exponent was a fraction. And so when I bring it down to be a normal number, it's again a fraction. It's not going to change. All right, so now I'm going to find the log of 0.5. We already had that. But here we go. So I still got this negative 0.19 is equal to 4 over H. But let's see here. I got the log of 0.5. We already had that. That is negative 0.3. All right, and again, I can't forget. There's my H there. All right, now here we go. I could really extend that like that. Well, I can actually go a little bit further here, because I can do 4 times negative 0.3. All right, so again, I got negative 0. Again, I'm just showing a lot of steps here, but let's see, 4 times negative 0.3, I get negative 1.2. And again, can't forget, there's my H in the bottom. All right, now I have a number equaling a fraction. So again, create a fraction equaling a fraction. All right, so that I can cross multiply. And so let's see, I'm going to have negative 0.19 times that H. All right, and that is going to equal 1 times negative 1.2. Well, that's going to be negative 1.2. All right, then my last step, divide by my numerical coefficient, which is the number in front of my letter there. So negative 1.9, so I got to divide over here by negative 0.19. And again, as you can see, a negative divided by negative, it's a good thing because you can't have negative time. I end up with 6 point, again, going to 2 decimal places, 32 units. T and H always got to be in the same units. And so the time went by was 4 days. So the half-life we're talking about is 4 days. So we got 6.3, our half-life is 6.32 days. Now, a practical application of finding out the half-life of an object is you can identify an object by its half-life. And as I mentioned earlier today, is that with radioactive material, carbon-14 does not hurt us. In fact, it's in us. but other forms of radiation are bad. And so if we find a material and I find out it's radioactive and you can figure out what material it is and figure out whether that material is dangerous or not. All right, so that is, just stop here.